here. In phasor analysis, I think you've had a talk on FLIM phasor, talk on spectral phasors, and here are some of the things we can do to expand the work on phasors. So I'll be talking about clustering. I'll be talking about the multi-component analysis methods that Lionel was mentioning in his talk. So clustering is a generic family of machine learning methods which go about given some data, tagging it and separating it into groups. So in this case, you have a two-dimensional set of points, and you say, I want 3 groups here. Well, the 3 groups are, the clustering step is to say, okay, this is one group, this is another one, this is the third group. So in this case, the label is the color. This can be a very complex problem, especially when data is mixed or when you have a high dimensional problem. But as you can see, two-dimensional problem, phasor kind of can look like this. So we have a direct application to unsupervised phasor cluster analysis. You've seen that you have a representation of your image. You have, for each pixel of the image, you map it to this two-dimensional space, the phasor plot. And you have some distribution of points here that you may want to cluster and see how it goes back to the original image. Traditionally, these people have done this manually, but it makes sense to find a way to do it automatically, robustly, and without the error of human-induced error, and to make it reproducible, right? So in this case, you see 2 clusters, you go back to the original space and you figure out that the pixels that belong to the right cluster are in the cytoplasm, and the pixels that belong on the left one is the nuclei. So we did this work on how to, or at first kind of a study on the different available methods in the literature. For that, we used synthetic data. We generated our own lifetime data in this case. So a bunch of points, simulated pixels with a load of photons each, and then drawing from lifetime distributions to map them in specific positions in the phasor plot. These are the 5 cases that we know the ground truth that we'll test the methods against. An easy case where clusters are super separated. A skewed case, which would be, say, some lifetime components and another component that is pulling everything down to the origin. Cases in which you have a big cluster overlapping smaller clusters, or lack of points, or a hard case where everything is mixed together. And then on the horizontal axis, I'm testing against all the different methods in the literature. You've probably heard of k-means or the same family of methods. These are based on distance to clusters. So you basically group them and measure the distance of each point to the center of the cluster, and you try to minimize that while maximizing the distance to the other clusters, and keep swapping them this way. There's other methods based on connectivity graphs, there's graph theory. Others based on kind of density. The main shift is kind of a tricky one where you throw stuff on a grid and you move the points of the grid and towards the points of more density. And DB-scan is a more modern approach, which is similar to that. And then spectral clustering is kind of an isolated guy here where it's based on eigenvalue decomposition, so you work in a separate space. And Gaussian mixture model is the one that I'm making the case that is the best for this kind of data. So as you see, I am reporting this number, the Jacquard index, which is unity when the clustering is perfect. So in the top case, they all succeeded. Every point is assigned to the correct cluster. And it goes below unity as you start to diverge from the ground truth. So, for example, in the skewed case, you see how the ones that are based on distances tend to mess up because, well, you see that the tail of this cluster here is closer to the centroid of the cluster below. So it makes sense that these are messed up. And you start to see other issues like the presence of outliers. So some of the methods allow for outliers. So even if you're looking for 3 clusters, the method may find that some points belong to none of the clusters. And a good example is this point down here, which is off. This is because it's off the density. So these guys are all at a highly packed and an isolated cluster. The method understands it as an isolated point. And well, as you see, they all have their strengths, and some fail where others don't. But I have marked the best performance in each case. So at the beginning, as I said, yeah, they all perform perfectly. And as you see, the one that consistently outperforms the rest is Gaussian mixture models. And there is a reason for this, which is the Gaussian mixture models assumes that your data is distributed in a normal distribution. So it's like you can model a Gaussian on top of your data. And that is exactly how the error of your distributions on the phasor plot propagates. So it makes sense to use Gaussians to describe your clouds on the phasor space. Okay, so what are Gaussian mixture models? Well, as I said, you're assuming that you can model your data points by a weighted contribution of, in this case, two-dimensional Gaussian distribution. So you have a sum of k Gaussians, each with its weight, omega, and g would be the Gaussian function that is put on top of your phasor space. It has a complex expression, which is basically a number times the exponential of a negative squared value. And if it were a single dimensional Gaussian, it would be the position squared. Since it's in 2D, these are vectors. So it's a vector times a matrix times a vector. And these parameters describe the position of your Gaussian. So you have some cloud that you want to model with this ellipsoid structure, and it has the weights. These are parameters you need to find. It has its centroid, so the vector that goes from the origin and tells you the mean position of your cloud. The covariance matrix, which describes the shape of this cloud, which is a combination of the standard deviations in each direction. It's this matrix here, so it's a standard deviation in the X or G if it's phasor analysis, and S direction or Y direction, and then the cross correlation of the two. And what you need to do is, given your set of points, attempt to find the best combination of these numbers that describe your data. There's a bunch of literature that refers to this. Very early on, the first hints at it is by Pearson over 100 years ago, applied to theory of evolution. And then it kind of became famous in the 70s when at the start of the machine learning revolution. But it's still an open problem, especially in regards to finding the correct number of clusters, so this value k. The typical algorithm that has been used for 30 years is the expectation maximization, which is an iterative process by which you throw a starting random values for these parameters, and then kind of shift it towards maximization of the fit. The good thing about it is that it always converges. So you simply run it, and then when there's no change in the parameters, you can stop there. Sometimes it converges to erroneous results, as we will see. So here's an example of it at work. Easy case, you have some data, you tell it you want 3 clusters, you start with random parameters, and the thing converges to find you these 3 clusters. So this is, again, it's an easy case. But here I can show you a harder case in which there's, again, 3 clusters, and they kind of mix together. Oops, sorry. And again, it converges, and very nicely indeed. And one of the good things about this method is that it is not a hard classification. It's soft in the sense that it gives you a probability. The weight that you obtain for each Gaussian allows you to then compute for each point the proportion of each of the 3 Gaussians in this case, which allows you to give kind of a half-half chance of some of the points. For example, these ones in the border between the clusters that are belonging to one or the other, right? A good example here is also these points which belong to the rightmost cluster, which, as you see, have been assigned a higher probability of belonging to the rightmost than the middle one, as you can tell by the kind of orangey shade of this color here. Okay, so let me show you some actual phasor data. All of this was all simulations till now. So this was what Leonard was talking about, this gene expression project that started here at UCI and then developed into a company. This was the first time that we started to use these methods to figure out ways to do automated analysis on the phasor space. So we have some transcripts labeled with 2 fluorophores. These are mRNA transcripts, and the phasor distribution has this shape here. Now, the number of points on the phasor plot depends on the number of pixels on the image. In this case, it's 256 by 256 images. You have in the order of 65,000 points on the phasor plot. You're used to seeing phasor plots more like heat maps. So you're basically drawing a 2D histogram on the phasor space and then kind of counting the number of spots in each of these little squares in the grid to build your phasor plot. But for our clustering methods, you need to go to the raw data. So have a list of 65,000 pairs of points and do the analysis over that data. So yeah, this is these labeled. We have 2 transcripts labeled with Alexa 647 and Atto 647. These are 2 dyes that emit in red, but have different lifetimes. So you have a single snapshot in red and you distinguish by lifetime. You run the clustering Gaussian mixture model and you obtain 2 clusters here that allows you to, as I said, go back to the original space and resolve one from the other. And again, there's also some points in the middle that you may want to discard, or at least you know that they're kind of you're not sure which of the 2 they belong to. Let me show you some other examples. Again, this is a single spectral band, so a single just emitting in the red in between 660 and 700. 3 dyes, all emitting in that region of the spectrum, but with 3 different lifetimes. You obtain the phasor plot, and you may think that there's 2, 3, 4 clusters here, but since we know that we have labeled with 3 dyes, we run the analysis for k equals 3, and this is what the algorithm returns. Go back to the original space, and it matches what you would expect, which is that lysosomes around the cytoplasm, the membrane dye is targeting the membranes, and you have the ethidium bromide, which is targeting the inside of the nuclei. And finally, maybe the final problem that we used this for, this was our publication in Nature Comms, in which we applied this for transcriptomics in a more broad way. We're using combinatorial labeling, where it's not like the first case, which you have 2 dyes labeling 2 targets. What we have here is the minimal working example for a combinatorial case, where you have 2 dyes labeling 3 targets. So you have an mRNA target labeled with a bunch of fluorophores of 1 type. Then you have another target they're labeled with the other type. And then you have a third target, which is labeled with a combination of equal proportion of the 2 fluorophores. So you would expect, again, these are the same fluorophores from the previous case. So it's Atto 647 and Alexa 647, both emit in red, but have different lifetimes. You would expect the third gene to have a phasor position which is in the middle of the other 2. So you have some theoretical position of the Atto 647 long lifetime, Alexa 647 short lifetime, and the 50-50 of the other 2. So target 2 should fall in the middle. And then you have some other phasor populations that are dragging your data into what probably is what we call as autofluorescence. So you have some other groups here that are pulling all this down to somewhere down here, but still you see the 3 clusters which correspond to the 3 populations in the data. If you model with the Gaussian mixture model, you obtain the 3 groups here, and you can go back to the original image and resolve the 3. The clusters that are marked here correspond to either 2 clusters together, 2 transcripts together that are labeled with different fluorophores and that are giving this mixed signal. So there's some pixels that contain photons that belong to 2 different targets, or it could be non-specific binding of some sort, but we think that it's most likely due to overlapping of our data. Yeah. And to finish off the clustering, I will talk about some of the limitations of the method. So the first thing is that you cannot model linear combinations. Going back to the previous, in this case, you have a bunch of pixels that can only have either pure signal from one fluorophore, pure signal from the second, or pure signal 50-50 of the 2. But there should not be pixels that have a gradual concentration between 1 and the 50-50 say. So you would not expect to find pixels that have 25% of the photons coming from here and 75 from here. The points in the middle are due to the noise in the phasor plot. It's the distribution of lifetime that has lack of photons, and then the distribution is not perfectly exponential, and you're spreading out from the true position, which is in the middle of these 3 points. But in some cases, you do have regions, pixels of your image that has a gradual proportion between 2 populations. This is an example. You would have, in this image, you have a population here and a population here, and there's a bunch of pixels that have gradual proportion from one to the other. This is not a proper Gaussian model distribution that you can model with a normal distribution. This is just a linear combination from one to the other. And the method tends to fail in these cases because it's trying to adapt a Gaussian on top of this when it's poorly, the fit is very poor. And the proof of this is that you go back to the original image and you see like it's labeling stuff that is not really anything. It's just a transition from the nuclear dye to the whatever is labeled on the cytoplasm. So this is one of the main limitations we have for phasor analysis. Yeah, these are the examples. The other one is finding the number of clusters, which is maybe not as relevant to us because you always know how many fluorophores you're using and what you're labeling your sample with. But it is relevant, especially when there's high autofluorescence in the background, or and other components that are contributing to your phasor data. So how do you choose the number of clusters? You'd say, okay, clearly you have three groups here, but I could also argue that if you put a Gaussian on top of a tiny Gaussian on top of each of the points on your data, that would be the perfect fit. So you have, I think it's 400 points on this simulation here. Instead of saying 3 clusters, you would say, the perfect model is 400 clusters. This is why there's been a bunch of methods related to establishing the correct number of clusters. And there's these criterions that tend to minimize, so they penalize the number of clusters at the same time as maximizing the efficiency of the clustering. So usually in perfect cases, you would expect to find a minimal in this quantity in the ideal case for your data. But since you have a bunch of other problems in your data, such as the linear combinations I was showing before, your data tends not to spread out perfectly Gaussian, so there's always error in your data, and normally you don't see a minimal, you rather see some angles. So what people tend to do is find the sharpest angle in the variation of these quantities. As the data, this is the example of one of the ones I showed you before, as it gets complex and complex, at the end it's just a smooth curve. So it's an open problem. Okay. I think that's about it for this. I don't know if anyone has any questions about these methods for the moment. Not yet. I will move on to the multi-component analysis. This is more about what Leonel talked about earlier today, and can also be applied to lifetime, but it's going to require a bit of, again, I get a bit of heavy math introduction here. You have seen the phasor transform for both lifetime and spectral microscopy. You have a list of photons, each one with its either time of arrival if you're doing lifetime, or its spectral wavelength if you're doing spectral measurements. And then you can plot all these photons as a histogram of the number of photons you have for each arrival time in this case, or wavelength. It will be here. So this could be a spectra, the color, or in this case it's the arrival time. This is your intensity as a function of time, or lambda, your wavelength. The phasor transform, maps this shape into a position on the phasor plot using these 2 quantities, which are the S and the G coordinates for your point on the phasor plot. These expressions here basically try to capture the shape of your curve using the sine and the cosine transforms. And there's a little animation here that tries to show how this happens. So this is your intensity as a function of time. you fit a sine function that fits exactly in your period or your spectral window that you're measuring it with. You multiply the two, so this is the product of the black curve times the red dotted curve, and then you integrate. This is the denominator, sorry, the numerator. So it's the product integrated over all the points. It's the sum, is this area, the yellow area. This is one number that gives you the vertical coordinate. You now do the same for the cosine. You fit it once in your period, you multiply the two, you integrate, and the number, which is the area, the purple area, is some other coordinate. Now, these two coordinates map to a position, which is the transformation of this curve onto the phasor space. You do this for each of the pixels in your image, and you have some cloud of data on your phasor spot, on your phasor plot. Now, the important thing here is you can use higher harmonics of the sine and cosine trigonometric functions. The higher harmonics consist in adding an n number here, so that your sine and cosine functions, instead of fitting once in your period, fit twice, 3 times, and so on. So here was the animation for one period, but we can do the same, adding 2 periods of your trigonometric functions. You see there's twice the bulbs here. And now the same curve, the intensity curve, maps to a different position on the phasor plot. And you can do the same for 3, 4, and so on. As you see, the positions tend to, as you add higher harmonics, they tend to shift towards the origin. And this is because the positive and the negative parts of the integral tend to cancel out. The more ups and downs you have, the more they are closer to each other. And at the end, at the limit where n equals infinity, everything goes down to 0. But in any case, you have a new transform, one for each n harmonic number. And this is the basis of the method to do the multi-component analysis that I'm going to talk about now. Other key concepts that you may have already heard today is that if you assume that your intensity decay is a pure exponential, so it has some tau, the lifetime, and you plug this quantity into the integrals here, and you solve this, you obtain the curve of a circle, which is the universal circle, which means that if you have a pure exponential, your data is always going to be on this circle. If tau is a small number, it's going to be to the right. If tau is a large number, it's going to be to the left. And if you don't have a single exponential, you have a combination of exponentials, your data point is always going to be inside the circle. So it's a linear combination of some points which are on the circle outside, which is the pure exponential components. And then you have also learned today that phasor addition follows linear algebra. So that if you have 2 components that are in some positions and you have equal contributions of the two, so 1/2 of you have some data that you have 1/2 of the photons come from this component here and 1/2 of the photons come from the component on the left. This means that you can see this as a vector addition in which it's the contribution of half the times this vector plus half the time this vector takes you to the mean position halfway across the line that joins the two. And this is true for any weights or fractions of these components. So if instead of 1/2 and 1/2, you use 3/4 and 1/4, well, basically you're saying that in this point here, 1/4 of the photons come from this component on the left and 3/4 come from the one on the right. So key concept number 3 is that if you are in the universal circle, so if you are a pure exponential, you can compute the higher harmonics analytically. That is not the case for the points that you have inside. But if you are on here, and this is harmonic 1, it's harmonic 2, you can calculate this using this expression here. Okay, so now, using all of this, what we're trying to do is, you're given some data, and you know that in that pixel, there's a bunch of photons that come from different number of components. You want to figure out how many of those photons belong to each of those components. So at that pixel, what is the proportion of photons that come from each of the pure components in your data? So like the example that I was giving before of the transcriptomics, you may have in a single pixel 2 RNA transcripts labeled with 2 different labels. And if you have your phasor data, you can figure out how many of the photons come from each of the 2 labels. So you can quantify the expression of your transcripts at the subpixel resolution. So in the case of a two-component problem, this is what I was showing you in the previous slide. You have some data point, the capital G and S. This is your data point, what you're measuring. And this is the lowercase g and s are the known positions for the pure components that are contributing to your sample. So you know that the G coordinate of your data point has to be a linear combination of the G coordinates of the pure components. The same applies for the S. The S coordinate of your data point is a linear combination of the S coordinates of the pure components. And finally, you know that your fractions should add up to unity. So you have to solve this system in which the lowercase g's and s are known values, the capital G and S are your data measurements, so it's also a known value, and what you want to find is the fraction of each of the components that contributes to your data point. In this case, you have two unknowns, the two omega-1 and omega-2, and three equations. So it's an overdetermined system. You can solve this. If you move to three components, again, it's the same system. In this case, three equations, three unknowns, determined system, one exact solution. But beyond this, in theory, there is no possibility of more. If you have a four-component problem, now you have four omegas you have to figure out, and you only have three equations. And here is where we come with the multi-harmonic method, in which we compute the second harmonic of this phasor distribution to obtain a new set of equations for the second harmonic. So now the four-component problem with one extra harmonic gives you a new set of equations which correspond to the capital G and S of the second harmonic and the lowercase g and s of the pure components in the second harmonic. You may think, oh, but these two polygons are the same. They look the same, but they're not really the same. It's a slight variation. This equation here is not a proportion of the one up here. There is a variation, and this is what allows to give you more information and to solve this problem. This is due to the nonlinearity of the lifetimes along the universal circle. So now you can solve this. So you can, in this case, you have an extra equation even. You can solve it by least squares, minimize the values of the weights that fit that, so that these equations match, and you obtain the weights for these values here. Again, using the fact that you can relate the second harmonic of the pure components to the first. So you can express G second harmonic in terms of G first harmonic, and so on, for the pure components. Okay, knowing all this, let me show you some data. This is some cells that we labeled with nucleotides. And I forgot to say, so yes, I'm talking always about pure components on the universal circle. Note that in this case, the pure components are no longer in the universal circle. So we don't have an analytic position for this. It's not like we look in the literature, what are the lifetimes of these components? What we did is actually measure the pure components by themselves. So we loaded a sample with only rose Bengal, a sample with only Nook blue, sample with only acridine orange, and a sample with only ethidium bromide, and measured their phasor positions. And once you have the four pure components, then you measure a fifth sample that has all four of them together. And then the method allows you to, for each pixel in the image, obtain the proportion of each of the other four. And in this case, we use this color method in which black would be a zero value of that pixel of the weight of the ethidium bromide. Pure blue would be unity. In this case, this was for the acridine orange, so the second component. This corresponds to the Nook blue, which is the third component, and this the rose Bengal. And at each pixel, you can figure out the proportion of each of the four fluorophores that are in that location, allowing you to do this decomposition or unmixing. Here's another example. In this case, it's not lifetime data, it's spectral data, but basically it's the same idea. You have some spectral measurement of a sample that has 4 known components in there. You measure the position of the components, which have their spectral locations in the phasor plot, and then you can unmix it to reveal the proportion of each of the components in each of the pixels. It's nice to see how the mitochondria that were barely visible here now start to appear as the third component, corresponding to the pixels that have a higher component of this guy here. You see the membrane here as well. So yeah, this is proof that kind of the method is pretty robust and powerful. And this is, maybe you've seen this earlier in Leonel's talk. This is the work that he was mentioning, in which we kind of expanded on this method for spectral analysis. This is like the slide that would summarize what we have done here. You have some, in this case, 5 components, 5 pure components, which are spectral leases in spectral data. So kind of a purple one, cyan, green, yellowish, and red. And then you concoct these 2 mixtures of these 5 components here. And these are concocted in a way that they match the same phasor position. So let me explain. For example, mixture 1 corresponds to 1/2 of pure component 2 and pure component 4, which correspond to the blue one and the orange one. So if you sum 1/2 of this one and 1/2 of this one, you obtain this black line here, which was like a double peak here. And then mixture 2 is a mixture of the other 3, which is some proportion of pure component 3 plus another value, which is dependent on this one here, so that they again add up to unity. And you have, well, some distribution, which is this triple peak. We choose this value so that the phasor position of these 2 falls exactly on the same spot on the phasor plot. Here's the ambiguity that you have in phasor analysis, that given a point on the phasor plot, you can't really tell what are the pure components that go to that point. So the same that I was describing as sum of distributions, you could say, okay, mixture 1 is the linear combination of point P2 and P4. And again, mixture 2 is the linear combination of these 3 here. You map all these points on the second harmonic, and it immediately resolves the data. It's separating it into 2 groups, in which you have clearly mixture 1 corresponds to the linear combination of P2 and P4, and mixture 2 corresponds to the linear combination of the other 3. Yeah, and to finish, we did also some work on kind of quantifying how this method performs as opposed to traditional linear unmixing, which is the technique that has been used forever in astronomy and for separating in the same pixel spectral components. And we found out that when this is a thing that is known, that in linear mixing, when the fraction of one of the components is kind of high, closer above, in this case, about 2/3 away, it tends to give more weight to that component. And we found out that using the phasor analysis, you kind of are slightly above linear mixing in that region of fractions. This is number of photons as a function of number of photons and the fraction of each component, which of the 2 methods perform. So in this here, it's the phasor method is superior, and here the linear mixing is superior. As you see, if you have enough photons above 100,000, all the methods work perfectly. Okay. Yeah, and about these unmixing problems, this is the end of it. This is now like an extension on this, which is how not only till now we knew the positions of the pure components, and we're trying to figure out what are the weights of those components, how many photons belong to each other. But the next step would be, can we find the fractions? Okay, first thing is, can we just simply add harmonics and have any number of components? So go from 4 to 5 to 6 to 7 and so on. And I remember going to Enrico and asking him, and he says, well, no way, this is not going to happen, because look at the way your harmonics spread out in the phasor space. As you add higher harmonics, everything converges to 0, everything is joined together. So no, we can't go up to infinite, any number of components. But the one thing that is true is that maybe if we just keep down to a few number of components, so 4 or 5, but can we find the fractions and the lifetimes of this small number of components? And we show that, yes, in certain conditions, you can also do that. So not only figure out what are the fractions of each of the pure components, also figure out the lifetime. If you have unknown, so this is what we call the blind multi-component method, in which you don't even know the lifetimes of your components. And this is kind of a heavy slide again. So you know that you can express the positions of the pure components on the universal circle. So you have some expression of the universal circle. What I showed you before, the key point number 3, you can express the higher harmonics of the components on the universal circle. These are the harmonics numbers. And let me show you a case for 3 components. So you have 3 components, which you don't know their lifetimes, so you don't know their phasor positions, you don't know where they lie on the universal circle. So their G's and S's are unknowns, and also you have the 3 weights, which are also unknown. So you have a total of 9 unknowns for a 3-component problem. Now, using the fact that you can relate unknown pure components are in the universal circle, therefore you can relate the S's as a function of G. So you reduce it to 6 unknowns, in which you have 3 G's and 3 omegas, because the S's are related to the G's. So you need at least 6 equations to solve this problem. So we're going to require at least 3 harmonics for a 3-component problem, which will give us 6 equations plus the last one, which is the one that the components add up to unity. So these are the equations that I showed you before. The only difference here is that now, before you had that this was a number that you knew, the location of the pure component on the universal circle. Now that is a number that you don't know. So you have a bunch of weights you don't know and a bunch of coordinates you don't know. So this is no longer linear equations. This is a very hard problem in which you have all the variables are products of each other. If you try to solve this analytically, it's a mess, especially because you're relating the S as a function of G, and there's a square root involved here because S is equals to the square root of this. So you can't do this by hand. So you have to resort to minimization problems, in which you kind of join everything into a single equation and try to minimize. So try to find the values that make this number, whatever it is, the combination of all these here, minimal. This is some surface that you have to minimize. And the solution that you're looking for is the combination of G's, S's, and omegas that give a lower value in this surface here. Let me show you some example. This is highly computational weight. If you want to consider you're doing this for each of the pixels in your image. So you're doing it in the tens of thousands, hundreds of thousands of times. You're doing this minimization problem. But nevertheless, we did succeed in doing this method here. This is again using the 3 nuclear dyes that we measured their lifetime separately in the order of 1 nanosecond, 2.5, and 4. And then we made a mixture of the 3 together. So this contains the 3, and attempted to recover the fractions and the lifetimes of the components at each pixel. And you do get very broad distributions so there's quite a lot of error in the lifetime evaluation, but still the peak positions of these distributions correspond to what you would expect. So notice that you have here 4.18 as opposed to 4.1, 2.9 as opposed to 2.5, and 0.7 as opposed to 0.9. So we published this work in which we did a 3-component problem, and we also did a 4-component problem, and show that it can theoretically be done, although you have quite a lot of error. And this is the other set of data that we showed in this work, which is, I think you may be hearing about this later on by Suman. This is a data from a collaborator that they have mice that have been fed low-fat diet and Western diet, high-fat intake. And they showed that there is a long lifetime species component in these sets of images due to the presence of this fat in the data. This looks here like basically oil specks on your sample. When I first saw this image, I thought it was just a dirty sample. They'd forgotten to clean the oil off the glass. But this is actually the liver chunk in which you have these gigantic balls of oil. They have a very long lifetime species component, and we showed that using our method, we obtained the same results as using traditional phasor analysis, and we obtained the proportion of the non-fat component. So we kind of unmixed the fat component to obtain the proportion of the other two, which are present there. Then if you map to the original image, you see this, we painted in yellow, this long lifetime species corresponds to all the fat here. And yeah, that's about it. I don't know if any questions here.